was worried that that other one was getting too long. This is part. So I hope you understood what I was talking about this polyatomic right here. You have to think about this polyatomic as being a single atom by itself, this phosphate with its -3 charge. And you also have to think about that the overall compound must remain neutral. So let's break this down. If I have 3 of these calciums, that's what this number right here means. I have 3 of these calciums, and each of these calciums has a +2 charge. 3 times this +2 means I have an overall +6 charge. And this 2 right here means I have 2 of these phosphates, and each one of these phosphates has a -3 charge. So I have overall a -6 negatives charge on this particular compound. And a +6 plus a -6 balance out and give me a 0. So this compound is overall neutral. All compounds must end up being neutral, or they cannot be called a compound. They're still an ion. That is what it's talking about. So in order for it to be a compound, it must stay neutral, or it must have the word ion still attached to it. All right? That's why when you're naming ions, you must be sure and put ions at the end. Now let's practice naming a few of these, because you're going to have to name quite a few. First of all, I gave you on Blackboard, I put a much larger flow chart of how to name everything from acids to polyatomics to molecular compounds to ionics. So first, here we go. It's a small little flow chart. Here's how to for naming ionics. Remember that if it's a cation, it's either going to be a metal or it's going to be the polyatomic ammonium. It is the only polyatomic that has a positive charge. Then it can be an anion, so it's either going to be a single atom like chloride or bromide or sulfide or oxide, or it's going to be a polyatomic like sulfate or carbonate, one of the ones I asked you to learn, nitrate, hydroxide, one of those. Then here's how you name them. The cation has only got 1 charge. It's going to be ammonium. It's always got a +1 charge. It's going to have the alkali metals. They're always got a +1 charge. The alkaline earth metals, they always have a +2 charge. Then there's some others that are listed here on this flow chart for you, like silver always has a +1 charge. Zinc always has a +2 charge. Aluminum always has a +3 charge. Then you have the transition metals that can be named with your Roman numerals. If you have to name those with the Roman numerals. You have to remember to name those with the Roman numerals. Then you have the anions, okay? And it goes into how to name those two. We're going to practice with these here in just a minute as well, okay? Do not forget that you're going to add the IDE to the ending of these. And if it ends in a polyatomic, you do not change the name of polyatomics except with acids. All right, let's practice naming. Let's see, that's going to be your best thing. You have MgO. So this is binary. I know it's binary because it's only got 2 elements in it. I've got magnesium and I've got oxygen. And so I'm going to name this. The cation is magnesium. The anion is oxygen. So magnesium stays the same. Oxygen turns to oxide. So this is magnesium oxide. And that's the name. Then, letter B here. I have aluminum right here. And I have the polyatomic hydroxide right there. So this becomes aluminum hydroxide. Now, I knew that this was a polyatomic because, first of all, it's not a binary compound. There's more than 2 capital letters. That makes it a ternary, a more than binary compound. And it has parentheses. That's another giveaway that this is going to have a polyatomic ion in it. All right. Then we get to even a more challenging one. This is iron. And as soon as I look up iron, iron is a transition metal, and so it can have more than one charge. And sulfate is a polyatomic. And here's these are the most, in my mind, the most difficult to write the names for. Of all of the compounds that there are, these are the most challenging. So here's what I'm going to do. I'm going to say, okay, iron here, and here's sulfate right here. I know the charge on sulfate is a -2, but also this 2 right here, where did that 2 come from? From that crisscross method that was used. So I'm going to uncross this. This was a -2 charge. Well, where did this 3 come from? It came from over here. So what is the charge on this particular iron? It is iron 3. So that must be included in the name. Now, if you name one with these Roman numerals that does not need it, that is not okay. So this becomes iron. It must have the Roman numeral. That's part of its name. And then sulfate. Iron 3 sulfate. Iron 3 sulfate. You only can include the Roman numerals when they can have more than one charge. You cannot just, oh, I'll just put it on all of them. No, you can't do that. Only if they can have more than one charge is that allowed. All right, here's some more. Here's some mercury 1 chloride. What does that 1 that's in parentheses represent? The 1 in parentheses represents the charge on the mercury. Please do not get it mixed up. That 1 in parentheses represents that's mercury 1, and so it can only have a 1 charge. I think this is a typo right here. Oh, it's got the 2 with the 2. So this becomes HgCl or Hg2 because mercury usually only exists as Hg2Cl2. And then this one here, lead 2, and then here's chromate. Now chromate is one of polyatomics, but it's not one of the polyatomics that I asked you to learn, so you can always look them up, and they are in your textbook on page 62, and you can just find them. And chromate is CrO4, and it has a -2 charge, so you can look it up. Here's Pb, and it has a +2 charge, and CrO4, it has a -2 charge. And look at this, since you have 2 of each, this one has a +2 and this one has a -2, it's already going to balance out. They already add to be 0, so you don't have to crisscross those. Your formula is just going to be PbCrO4. This is lead 2 chromate. And then you have potassium hydrogen phosphate. Again, hydrogen phosphate, that is a polyatomic, but it's not one that I asked you to learn. But again, you can look it up, and here's its formula along with its charge. And so potassium has a +1 charge. Hydrogen phosphate has a -2 charge. So when you get ready, these will not cancel each other out. They will not add to be 0. So my compound will not be neutral. Therefore, I have to use the crisscross method, and I get K2HPO4. And I do not need parentheses around here because I only need 1 of this polyatomic. Now, if I were to need more than 1 of this hydrogen phosphate, I would need parentheses around the entire thing in order to show that that's the entire polyatomic I need more than one of. That's important that you use parentheses around your polyatomics when you need more than one of them. Let me go back and show you what I'm talking about. For example, notice that in this aluminum hydroxide right here, notice these parentheses. If you just put AlOH3 like so, this 3 is only showing that you need 3 hydrogens, and that's not true. You need 3 of the entire thing. So you must be sure you use parentheses around polyatomics when you need more than one of them. All right, and then I'm going to go very quickly through this naming, this section right here, because I really did touch on it when I was talking to you about the polyatomics. Oxoanions are anions that contain oxygen, and they are always going to be polyatomics, and those are polyatomics that contain some other element along with oxygen. And because they can have some oxygen in them, oxygen can share. Remember, that's what polyatomics are. They're covalently bonded, which means they're sharing. They can share in more than one way, like carbon monoxide and carbon dioxide. Mind you, those are not polyatomics, but they can share in more than one way, and so they can have different charges, and therefore they're named differently. And depending on how they're shared, they're going to either be named ATE, 8, or ITE, 8. And they can also be named with a per in front as a prefix. So oxoanions are going to, like perchlorate and perchlorite are examples of these oxoanions. And that's all I'm really going to say about that. And you can study up on those, but they're not the more common ones. Some of the more common oxoanions are sulfate and sulfite and nitrate and nitrite. But as long as you know that's what they are, I'm fine with you knowing that. More importantly to me is the oxoacids, because you need to learn how to name them. And I'm going to go with you how to name acids that contain polyatomics right now. So this is where we're going right now. If you have an acid that contains a polyatomic ion, it's going to be a ternary acid instead of a binary acid. So they are named very differently. If you have an acid, remember all acids are going to start with hydrogen. It's going to be hydrogen and then something. So let's just talk about this. If you have, for example, let me give you 2 examples other than this right here. They give you these 2 with chlorate and chlorite. So this becomes chloric and chlorus. But let's give you 2 more. Let's give you H2SO4, and let's give you H2SO3. This SO4 polyatomic is sulfate. This SO3 polyatomic is sulfite. And if you were to name these 2 using these directions right here, and acids based on the 8, you change the ATE to IC to ic. So this, you do not use the word hydro when it's got a polyatomic. So this hydrogen sulfate becomes, you change sulfate to sulfuric. So this becomes sulfuric. 8 turns to ic, and then you write the word acid. And this is sulfite, so this one right here becomes sulfurous. Ite becomes us. uric acid. And you do not put that word hydro on it. Okay? Right. And then this, where I'm going next is with hydrates. And this is probably the last thing that I'm going to really talk to you about. Hydrates are just what they said. They're compounds that have some water molecules that are actually built into their structure, incorporated into their their atomic structure, into their crystalline structure. And some of the most common would be like Epsom salt, magnesium sulfate, hepta, right here, this. Is hepta right here. That means 7. This has 7 waters that are actually built into the crystalline structure. And you can actually drive that water off by heating this right here. I'm sure that's copper sulfate, and there it is with it dried out. So that's the difference in what they look like. And these waters are actually part of their structure, and so they are called hydrates. When you're figuring out their molecular formula, you must incorporate this water as part of their molar mass, And so here's some common examples of that. And that's all. I'm going to leave you some homework and quizzes now.